In this video, I want to demonstrate the memoization algorithm design technique by applying it to the word separation problem. Last time we focused on bottom-up dynamic programming algorithms, where we solved a sequence of increasingly larger subproblems. And when solving larger subproblems, we could make use of the fact that we had already computed the optimal value for smaller ones. Memoization is a way of doing top-down dynamic programming, where we start with the largest problem and recursively solve subproblems, but along the way we save the results of smaller subproblems so that once again we can make use of those optimal solutions later. To demonstrate this approach, we'll consider the example problem of word separation. To motivate this problem, suppose you were working on a creative writing assignment and a find and replace mishap somehow deleted all of the white space and punctuation from your story. At some point, you'll need to go back and actually recreate the story, but before it's worth doing that, you should at least determine whether the thing you wrote could have met the required word count. So we're given as input a string, which is some English text with all of the white space and punctuation deleted so that it's just a sequence of lowercase letters. We also have access to a dictionary that lets us look up whether a given string of characters is a word. And our goal is to determine the maximum number of valid English words that the string could be split into. So for example, if the input string were once upon a time with the spaces removed, the maximum possible word count would be 6, because we can split that string into 6 words like this. A first idea we might have for solving this word separation problem would be to try a greedy algorithm. And the obvious greedy algorithm here is to scan the text in order and put in word separations wherever we find a completed word. If we were to run this algorithm on our example story, we would look at the first character, determine that O is not a word, and proceed to the second character, at which point we would recognize that on is a valid word. We would then split the string and continue looking for words that begin with C. But C isn't a word, and CE isn't a word, and CEU isn't a word, and in fact, as we proceed through the remaining letters, we never find a valid word beginning with C. And so, our greedy algorithm doesn't actually give us a correct solution. If we took this approach, it's clear that we can find places where there is a word so far, but we would rather have made the split later in order to get valid or more words from the rest. Which means that we shouldn't be making our decisions greedily. We should have some ability to reconsider those decisions later. Another approach we might try would be a divide and conquer algorithm. With divide and conquer algorithms, we want to split into subproblems and solve those recursively. But we clearly can't just split the string in half every time, because that often won't split on a word boundary. Instead, what we could do is look for a valid word from the beginning of the string, make a split, and recurse on the rest of the string. But we could also continue looking for longer words from the start of the string, and likewise recursively solving the rest for any additional words. And this gives us the word count algorithm that I've described in pseudocode here. Our function takes the story and an index at which to begin, and it first checks if the rest of the story starting from that index is a word in the dictionary. And then for each possible index at which we could split the remainder of the story, we're going to consider whether the characters from the beginning index to the split index constitute a word in the dictionary, and if so, we will recursively count the words in the rest of the string. And the word count from the beginning to the end is 1 for this word we found at the start, plus however many words we found in the rest of the text. Over all of our different splits, we will end up choosing the maximum word count that we find and returning it. The base case of this recursion happens if we end up with a length 1 string, because then there will be no splits from begin plus 1 to the end. And so this for loop will not execute, and we will simply return 1 if that 1 character string was a word, and minus infinity otherwise. And because the recursive calls return minus infinity, even if the first part was a word, if we don't find a valid split of the rest, we'll get minus infinity, and we won't pick that as the best word count unless there are no other options. So this seems like a valid algorithm for the word count problem, and you should try sketching an inductive proof for its correctness. But let's think about how much work this algorithm is doing. If we ran it on our example string, we would loop through the characters, and each time we find that the characters so far are a word, we will recurse. So we'll first recognize the word on, and we will recursively solve the word count of the remainder, and then we'll recognize the word once, and recursively count the words in what remains. And so here we have 2 recursive calls that are heavily overlapping and could potentially duplicate a lot of work. In this case, it turns out not to be too bad, because as we saw before, the recursive call starting from C will sputter out quickly, not finding any words at the start of that string. But we can clearly see other examples where a recursive call starting from the U would find the word up, and it would also find the word upon. And so, for everything in the entire rest of the story, we would have one set of recursive calls that began with up, and another that began with upon. And so all of those recursive calls are being duplicated. So in the worst case, if our story has lots of substrings like upon that have multiple ways they could be split into valid words, then every time we have such a case, the number of recursive calls is going to double, and we could easily end up solving an exponential number of subproblems. So to avoid this potential for an exponential explosion in the number of recursive calls, we turn to memoization. The key idea of memoization is that if we have a recursive algorithm where there is potential for the same subproblem being solved multiple times, we should avoid duplicating the work by saving the result the first time we solve the subproblem and just looking it up later instead of recomputing it. Our recipe for accomplishing this is to add at the top of each recursive call a check for whether this subproblem has been solved before, and to add at the bottom of each recursive call a line to store the result in a global table so that we can look it up later if we encounter the same subproblem. So let's make these modifications to our word count algorithm. So now our memoized version of the word count algorithm will, at the end of each recursive call, leave itself a memo saying this subproblem, starting from the beginning index, has been solved before, and here was the result. And at the start of each recursive call, we're checking whether there is a memo about this subproblem, and if so, we'll just grab the result that we already computed and avoid doing all of the recursive work for this subproblem. The key reason this can make such a big difference is that any case where we're resolving an existing subproblem now becomes constant time, whereas before it would have not only required looping through the rest of the string, but also making additional recursive calls. And when we cut off these recursive calls, we potentially cut off additional branching. And as we'll see, if we can avoid the possibility of multiple branches duplicating work, we can completely prevent the cases where this algorithm makes an exponential number of calls and get our running time down to big O of n squared. So next I'd like to trace through the execution of this algorithm, but first we need to think about what data structure are we using to store this results table. In practice, you might pick a hash table, but to guarantee that we have big O of 1 lookups, we'd rather allocate an array of known size that can definitely store all the possible subproblems. And since our subproblems correspond to indices in the string, we can simply allocate an array with length equal to that of our story, and if we make a recursive call starting from a particular index, then we will check that entry in our table. But since our subproblems correspond to indices into the string, let's also use that index to find a subproblem in our results table. When we initially call this function, we will give it the string and the beginning index of 1 to say we want the word count for the entire string. And so we are initially solving this subproblem. So our first call is on a beginning index of 1, and we find that the entire story doesn't constitute a word, so far our best number of words is -infinity, and now we consider different possible splits starting from begin plus 1. If we make our split at 2, then the substring before the split is just the letter O, and note that I've fixed our indexing here to correspond. And since O isn't a word, we skip the if statement and go on to the next iteration of the loop. With a split of 3, we do find that on is a word, and so we will make a recursive call. In this recursive call, we were given a beginning point of index 3, and as we discussed before, we'll find that there are no words starting from the C, which means that we will have initialized words to -infinity, and we'll never find a way to make it better. And when we get to the bottom, we will return -infinity, and we will store that value in the results table. Back in the initial call, we get -infinity for the rest, and so that's not better than what we have so far, and we continue. And on a split of 4, O and C is not a word, so we continue, and get to a split of 5, where the characters before the split spell the word once. This means that we'll recurse, passing in a beginning index of 5. The substring starting at 5 is not a single word, so we initialize words to -infinity, and consider each subsequent split. With a begin of 5 and a split of 6, we're left with just the letter U, which is not a word, so we continue, and find that a split of 7 gives us the word up, meaning that we need to recurse with a beginning index of 7. On that recursive call, the rest of the story is not a word, so we initialize to -infinity. and then we loop until we find a split index that gives us a word, which will happen at 9 when we get the word on. We recurse here. The rest of the string is not a word, so w is minus infinity. And we proceed until we find a split that makes a word, which happens on the very first split we consider of 10. When we recurse on 10, we find that time is a word in our dictionary, so we initialize words to 1. But we should keep looking in case there's a way to split this into more words, and we find that with a split of 12, ti spells the musical note T, and starting from 12, we again see a valid word, me, and we complete our loop having found no other valid splits. So we end up returning that value of 1 and storing it in our results table for the current begin index, which is 12. When this recursive call returns, we're back in the recursive call that started at t, and we found a split into ti and me that gave us one word in the rest. So now, rest plus 1 is bigger, and we update our number of words to 2. We keep looping, but the last possible split doesn't give us a valid word, so now we can store a word count of 2 and return it. This brings us back to our recursive call executing from begin index of 9, and we got back a count of 2 for the rest of the word, plus 1 for the single letter word A. So words updates to 3, and we continue with subsequent indices. At index 11, we have a valid word at, and so we will recurse on this index. The remainder of the story from here is not a word, so we initialize to minus infinity. But when we start looping, we see that I is a word, and so we recursively call on 12, but that call finds a result in the table and immediately returns it, which means that we update w to 2 and proceed, but we also find a valid word, I'm, since remember we also lost punctuation, meaning that we need to recurse on index 13. But E is not a word, so we initialize to minus infinity and have no iterations of the for loop, so we immediately store that in our results table and return it. Since that result was worse than what we had found before, starting at I, we don't update our word count, but now we're done looping and can return from this recursive call. We're now back to our call at index 9, and we got back a value of 2 for the number of words in IME. So rest is 2. We add 1 for the word at, but that's the same as the number of words we already had for this call, and there's no need to update. For indices of 12 and 13, we don't have a word starting from A, meaning that this recursive call is done, can store a value of 3 in the results table, and can return. So we come back to the recursive call that started from index 7. The rest value we got back was 3, we add 1, and that's better than minus infinity, so we update our word count. Subsequent indices in this for loop give us substrings ona, onat, onati, and so on, none of which are words. And so we will get to the bottom of this recursive call, store our best word count of 4 in the table, and return. Bringing us back to the recursive call that started from 5, where we have 4 words in the rest of the list, plus 1 word for up, and we update our word count to 5, and continue considering additional splits. A split at 8 gives us UPO, which is not a word, but a split at 9 gives us upon, which means we need to make a recursive call. And if we hadn't memoized, this is where we would be duplicating an enormous amount of work. But instead, because we saved the result from calling on index 9 last time, this immediately sees a value in the table and returns it. And so with just a single constant time lookup, we are back to our outer call, knowing that there are 3 words starting from the A. That means the value of rest is 3, but 4 is not larger than the word count we already had, so we keep looping and consider other substrings starting from the U, but none of those are words, and this recursive call can return. Before returning, we store our word count of 5 in the table, and we give back to our top-level call a word count of 5, to which it adds 1 for the word once, and we update our word count to 6. We continue our for loop at this level, looking for additional words from the start, but once a, once up, once a po, and so on are not valid words, and so we'll eventually reach the end of our loop, store the result in the table, and return a word count of 6, which, as we saw, is the best answer for our example problem. If we do a worst-case analysis of the running time for this algorithm, we should think about how many subproblems are we solving, and how much work does it take to solve each subproblem. Here, we ended up solving 8 different subproblems, but in the worst case, we might have to fill in this entire table. But big O of n subproblems to solve is far better than having an exponential number of recursive calls if we don't memoize. In addition, to solve each subproblem, we have to loop from the beginning index to the end of the string, which means that for the subproblem at b, we are doing big O of n minus b work. And since b ranges across the entire string, these loops will take big O of n work on average, giving us a big O of n squared overall running time. Finally, it's worth noting that over the course of our execution, we filled in most of our results table, and in analyzing our total amount of work, we counted the number of subproblems we might have to solve, and so we could absolutely have written our word separation algorithm to solve these subproblems starting from the smallest and working our way up, resulting in a bottom-up dynamic programming algorithm. This insight holds in general. If we can write a top-down memoization algorithm, we could translate that into a bottom-up dynamic programming algorithm. And also, for the bottom-up dynamic programming algorithms we saw last time, we could just as easily reframe them as top-down memoization. Better still, this means that we can use the same tricks we developed for dynamic programming if we want to save the decisions we made along the way. In our description of the problem, we just wanted to know the maximum word count, but if we had a second table where we stored the split that was best, then at the end we could trace back through that second table and find what was the best sequence of splits that gave us our maximum word count, and use that to output the actual split into words, which you could then use as a starting point for reconstructing your story.